Hello. I would now like to talk about part 9 of my series, Essential Theorems for Harmonic Astrology. So let me share my screen and we'll get started. This will take just a minute. Again, I have to get rid of some panels so I can see what I'm doing. We're just about there. Okay, and I think we're ready. So this is Essential Theorems for Harmonic Astrology, Part 9, Quantitative, Cancellation Theorems. We'll now look at a few of what I call cancellation theorems. Also, I'll make use of lemma 1 that I proved back in part 6 of this series, and so below is a reminder of what lemma 1 says. And it says if n is a natural number and q and p are positive rational numbers, then n times parentheses q modulo p parentheses close, and then that whole thing modulo p is just equal to n times q modulo p. As long as n is a natural number and q and p are positive rational numbers, this equality holds. And it allows me to just simply multiply n times q and simplify the result modulo p just once, rather than having to do it twice. Okay, now let's move on to theorem 10. If theta is a R harmonic angle, and if R equal n times q, where n is a natural number, and q is a positive rational number, then n times theta modulo 360 degrees is a q harmonic angle. Okay, since theta is a R harmonic angle, we have that theta is equal to k times theta sub r modulo 360 degrees, which is equal to k times 360 degrees over r modulo 360 degrees for some natural number k, and where theta sub r is the root r harmonic angle. Hence, if r equal n times q, then by lemma 1, n times theta modulo 360 degrees is equal to n times k times theta sub r modulo 360 degrees, and then that whole thing in brackets modulo 360 degrees. This, in turn, is equal to n times k times theta sub r modulo 360 degrees, which is equal to n times k times 360 degrees over r modulo 360 degrees, which is equal to n times k times 360 degrees over nq modulo 360 degrees. Notice that we can put nq here since that is equal to r. So that replaces r. And let's see, what else might I say before continuing? Well, theta here, it is an R harmonic angle, so it is some natural number multiple of the root R harmonic angle taken modulo 360 degrees. So that's where this second part comes in. Okay, now continuing from this point, if you cancel out the n's, this is equal to k times 360 degrees over q modulo 360 degrees. But this is basically how we define a q harmonic angle. So therefore, going up to the top, n times theta modulo 360 degrees is equal to this thing here. And so n times theta modulo 360 degrees is a q harmonic angle. And that's it. That works. Okay. So I call this cancellation because R is equal to n times q. We're looking at R harmonic angles, but we multiply that angle by n, and that cancels out the n here, leaving us with a q harmonic angle. Okay, corollary 10.1. If theta sub r is equal to 360 degrees over r, modulo 360 degrees is the root r harmonic angle, and if r is equal to n times q, where n is a natural number and q is a positive rational number, then n times theta sub r modulo 360 degrees is the root q harmonic angle. And to prove that, you can simply repeat the proof for theorem 10 with k equal to 1. And now here's another cancellation theorem that this time involves both addition and multiplication. Theorem 11. If an angle can be written as theta equal to m times theta sub r plus n times theta sub q, where theta sub r and theta sub q are the root r and q harmonic angles respectively for positive rational numbers r and q, and if m and n are natural numbers, then we have that r times theta modulo 360 degrees is just equal to r times n times theta sub q modulo 360 degrees. So when we multiply this angle theta by r and reduce the result modulo 360 degrees, you're basically canceling out this first term, which is the one that gives us an r harmonic angle. Well, let's look at the proof. Since r times m times theta sub r modulo 360 degrees is equal to r times m times 360 degrees over r modulo 360 degrees, and now you cancel out the r's, and this is equal to m times 360 degrees modulo 360 degrees. But since m times 360 degrees is a natural number, multiple of 360 degrees, this thing modulo 360 degrees is equal to 0 degrees. And from all that, it follows that r times theta modulo 360 degrees is equal to r times the first term up here plus r times the second term up here, modulo 360 degrees. And we just saw that r times this first term is going to wind up being a multiple of 360 degrees. So when we calculate the thing modulo 360, there is no non-zero remainder for this term, and we're just left with the second term, which will be r times n times theta sub q modulo 360 degrees. So that first term essentially got canceled out. Now, consequences of our cancellation theorems are that 2 times any 6 harmonic angle will be a 3 harmonic angle, since 2 times 360 degrees over 6 is 360 degrees over 3. And 4 times the sum of a 4 harmonic angle and 3 harmonic angle computed modulo 360 degrees will be equal to 4 times the 3 harmonic angle computed modulo 360 degrees. An example of the latter is 4 times 210 degrees modulo 360 degrees, which is equal to 4 times parentheses 90 degrees plus 120 degrees modulo 360 degrees. 90 degrees is a 4 harmonic angle, so multiply that by 4, it gets canceled out, and you're just left with 4 times 120 degrees modulo 360 degrees, which turns out to just be 120 degrees once you simplify it. And now, before going any further, let's prove a general theorem regarding the sum of 2 angles. My. This one looks a little longer. Theorem 11. If an angle theta can be written as theta equal to k sub r times theta sub r plus or minus k sub q times theta sub q, where theta sub r, theta sub q are r and q root harmonic angles for positive rational numbers r and q, and natural numbers k sub r and k sub q, respectively. And if n is also a natural number, then n theta modulo 360 degrees is equal to n times k sub r times theta sub r modulo 360 degrees plus or minus n times k sub q theta sub q modulo 360 degrees, and then this whole thing in brackets, reduce modulo 360 degrees. Well, when you have a long, complicated proof, always begin by saying clearly, as if it's all just so obvious. So clearly, n times theta is equal to n times this sum or difference. You can distribute the n, you get n times k sub r theta sub r plus or minus n times k sub q theta sub q. And that is going to be equal to w sub r times 360 degrees plus theta sub capital R sub r plus or minus some w sub q times 360 degrees plus theta sub capital R sub q, where w sub r and w sub q are whole numbers, and theta sub capital R sub little r and theta sub capital R little q are the remainders after dividing each of these expressions here, respectively, by 360 degrees. So that is what we're trying to do here. Whatever this is, we're saying you can divide this first term by 360 degrees, and you get some remainder over here. And you can divide the second term by 360 degrees, and you're going to get possibly a different remainder over here. And so each of these products can be written as some multiple, some whole number multiple of 360 degrees plus the respective remainder. Okay, notice too that n times k sub r times theta sub r modulo 360 degrees, that is going to be equal to this expression modulo 360 degrees. And n times k sub q theta sub q modulo 360 degrees will be equal to this expression modulo 360 degrees. And this is all going to reduce to just the remainder term here. And I may have skipped over it up here, but this expression here, modulo 360 degrees, also reduces to just this remainder term. Therefore, n times theta modulo 360 degrees, that's what we're starting with up here. It's going to be n times this product plus or minus n times the second product, modulo 360 degrees. That will be equal to this expression plus or minus this expression, whole thing modulo 360 degrees. And in each of these expressions, you have terms which are whole number multiples of 360 degrees. So when computed modulo 360 degrees, they're going to disappear, and you're just left with the sum or difference of those two remainder terms, modulo 360 degrees. And that is going to be equal to, let's see, n times k sub r theta sub r modulo 360 degrees. Let's go back up here. Theta sub r, that's equal to this right here. So I just put that in there. And let's see. Oh, here's a little typo. I'll change that later. This should be theta sub r sub q. This expression is going to be equal to this right here. N times k sub q theta sub q modulo 360 degrees. So this plus this, but change this little r to a little q, that is going to be equal to this whole thing, modulo 360 degrees. Okay, always a typo of or two to correct. Sorry about that. For an application of Theorem 11, suppose that we have two planets that are 125 degrees apart. Then most astrologers would probably say that the two planets are trine one another with a 5-degree orb. Thus, we can write 125 degrees equal to 120 degrees plus 5, where 5 degrees is the root 72 harmonic angle, and any natural number harmonic of this angle can be thought of before reduction modulo 360 degrees as the sum of a 3 harmonic angle and a 72 harmonic angle. 120 degrees is our 3 harmonic angle, 5 is a 72 harmonic angle. In particular, in this example, the error term, the orb, will always be based on a 72 harmonic angle, just so long as we're computing a natural number harmonic of 125 degrees. Okay, so that's always very interesting. If you multiply 125 degrees by any natural number and then reduce it 300 modulo 360 degrees, you're always going to wind up with a 3 harmonic angle plus a 72 harmonic angle. Okay, it looks like that is it for part 9. So let me stop sharing my screen here. And I'm back, but I look very fuzzy. So let me remove my camera and see if I can fix that. Okay, there is such a thing known as fuzzy math. So maybe that's why I sometimes look so fuzzy. Okay, well, I hope you followed that and enjoyed it. And I hope you join me for the next video in this series. This is for people who like both astrology and mathematics and feel comfortable doing proofs. Uh, some of these rules are things that people have just sort of figured out they figured it out by the seat of their pants, but someone needs to sit down and do rigorous proofs of these rules. So that's what I'm doing. And when we do that, we get a deeper understanding of what's really going on. And we also discover things which are not so obvious. Well, that's it for now. I hope you join me again in the future. But for now, I'll just say so long and be well.